Okay, now tomorrow, if you're aware, tomorrow 5:30 to 7:30, on first floor, second floor, third floor Mets, right? There's going to be these little things in the lab that are going on, tours, of all the new facilities and stuff. It'd be a great time to bring, it's supposed to be free food, if I remember this correctly. Someone might know more than me, but I'm pretty sure free food, free barbecue and stuff. It's a great time to bring family, friends, right, and just let them see what's going on. Like Guffey's going to have a bunch of snakes and stuff set out. Dr. Hall's going to have some stuff. Chemistry's going to have some stuff set out. Math is going to have some stuff set out. So 5:30 to 7:30, just roam around and see what's going on. Okay. I think I sent you an email on it too, right? Okay. So activities. What's the big deal with activities? Well, there's some general ideas. That ions interact with each other in solution. That's what some of these pictures are trying to say that. If we use concentrations, we're assuming these ions don't interact. In other words, when you say concentration, you just mean moles per liter. And for reactions, I mean, things actually have to collide or not. Do they have to interact? If A is going to interact with B, do they have to actually get in physical? Just got to be. Well, if a reaction happens, they actually do. Molecules, things got to come together, do their thing at the right arrangement. They have to come together at the right energy, right? Some right rotation. You start talking about enzymes and proteins. Then you have all these configurations that are important. But physical interaction, it absolutely has to happen. Well, so that's what you're saying when you say mole concentration. That this is the concentration of this. This is the concentration of that. You start talking about rate laws. You're talking about limiting reactant problems and all that stuff. And we use concentration every single time. Right? Our whole life we've been using concentration. Your whole every chemistry course you've ever used. Concentration. Concentration, concentration, concentration. Moles per liter. So what's the problem? Right? That means everything we've been doing up to this point, and it seems like I say this in more than one course, it's bullshit. We have to use activities. Why? For everything. When you're talking about rates, anytime where you use concentration, we're talking about, okay, you have this much reactant, how much product we can get. You had limiting reagent problems. You had we use concentration for everything. You have to use activities. Why? What's wrong with molarity? The problem with molarity is what I was trying to get at, saying that molarity is moles per liter. A mole is actually a number of things, right? But that's saying a number. It's 6.022 times 10 to the 23rd. Those 6.022 times 10 to the 23rd items have to actually interact with these items at the mole level. Numbers. This is interacting with that. Actually counting them out, like accounting. Well, they're not going to interact. Stuff gets in the way. What gets in the way? What gets in the way? Okay, let's think of it. Let me get a little pointer here. These little tan balls have to interact with these other guys to make this stuff. So instead of going this way, they're going the other way, right? The dark brown ones have to interact with those. Or think of it this way, or think of it as a drug and blood, whatever. Two things have to interact. But what gets in the way? If it was just these little, what are these supposed to be? Water molecules. If it's just water, they can't get in the way. I mean, yeah, everything is solvated. It's kind of canceled itself out. But what if you have other stuff there? Right? You have throw in some of these green and purple balls in here. Right? They're going to get in the way. Things that have a charge get in the way of other things that have a charge. You can't stop it. And the solution has no idea what's what. What's green, what's blue, what's brown, what's tan. No. It just, everything gets in the way. It's all clumped up. For stuff that if these guys didn't have a charge, if they weren't ions, concentration works great. Because this stuff doesn't get in the way. It's kind of like, I don't know, I have to use the terminology. Chemical environment. ionic atmosphere, you start talking about this stuff. If you have just nice pure water and pretend water doesn't fall apart into H plus and OH minus at that billionth level, it doesn't fall apart. All you have is pure H2O molecules floating around, right? And then you have some ions. They're going to interact, but throw in some other ions. They're going to get in the way of the two ions that you want to interact in the first place. Or this enzyme is going to interact with this guy. But as long as things aren't charged, you don't care, right? Because if something doesn't have a charge, it doesn't care what the ionic atmosphere is, how many ions are in there. It doesn't care. It doesn't have a charge. It doesn't interact. Just as well be more water. It doesn't know. So the problem is with ions, and that they interact with one another, and you can't stop it. So, for example, if you have glucose doesn't have a charge. Using concentration is great. It doesn't hurt anything. But if you're talking about ions that have a charge, now sodium and chloride are very simple, but there's a lot of compounds. We just talked about a lot of acids and bases. They have those conjugate acid, conjugate bases, they all have a charge, every single one. So imagine instead of having a sodium ion and chloride ion, you have something really important in there, some vitamin, some weak acid vitamin or something. It's going to really affect the ionic atmosphere in your blood. Is really going to interact. It's really going to affect the ability of that vitamin to go where it's supposed to go in comparison to it being pure water. So let's try to put things maybe more in a little different perspective than this big, broad picture. I changed this just this morning, but you have the general idea in your outline. So here's some solubility rules. Right? I figured someone really wanted them, so here they are. Okay. So, Pablo. You still have them. Pablo's going to tell us how to read this. Okay. Using this dealie that we've got here, what would be an example of an insoluble salt? What would be the formula of an insoluble salt? See if you can figure out how to read this. Give me a chemical formula for an insoluble salt. Okay. Okay, he wants to mess with cyanide. Where is cyanide? I can see cyanide down here. Oh, there it is. Oh, okay. Cyanide, it says cyanide falls under the soluble stuff. So if you want to mess with cyanide, you better find an exception. Oh, dang. Doesn't have any. Let's try a different compound. Adriana. She wants to mess with phosphates. Okay. Oh, man. You can pick most any cation, put it with phosphate, and it's going to be insoluble. Just don't pick what? Just don't pick any of these guys. Right? Okay, so she said a phosphate. Where's my little pen? PO4 negative 3. So give me a cation, Danielle, and just don't make it one of our alkali metals or ammonium. Would be a possible cation. So lithium, but that's in the alkali. I wish they would say group 1, right? Because whoever calls these alkalis. Do you remember? What is group 2 called? Brownie points, you remember? Alkali earth. We always say group 2. I never use alkali earth is too much to say. Okay. So calcium would work, right? That's not an alkali metal. So we could throw calcium in there. You could pick any metal. Copper 3, iron 2, vanadium 5, right? Zirconium 2, right? Because these guys, the transition metals, it's kind of, I'm just making this stuff up because they can pretty much take whatever charge they want. There's only a few like zinc and aluminum that are fixed. But, so here's an example. Do you remember the trick to make the formula? What do you do? Yeah, there's got to be a word for that. The charges go subscripts. The switcheroo, right? You do the switcheroo. There's got to be a name for it. I don't know what it is. Diagonalize them. I don't know. Switcheroo sounds good to me. Okay, so there's an example of an insoluble salt. Okay. So we have some calcium phosphate. We go to the shelf, we get it, we dump it in the water, and we could look up its KSP, and we could calculate the X in ice to get the solubility if we wanted. And we get whatever number. How could we increase that number? Now, when we get X in ice, we're using concentrations, right? 'Cause that's the only thing we know. But you can increase the solubility, and this is where concentration is going to screw you over. I have that solution, and I calculate my solubility, just whatever number it is. 1 times 10 to the negative 6 molar. Fine. Just pretend that's my solubility. I'm going to dump in some potassium nitrate. I'm going to dump in some sodium chloride. I'm not dumping in any common ions at all. All I'm doing is increasing the ionic strength, increasing the ionic atmosphere, having more ions per unit volume in the chemical environment, right? I'm physically changing water. It's not an environment that's, they got this kind of polar H2O molecules. No, I've got bloody ions, plus and minuses all over the place. The environment has completely changed. Is it going to dissolve that stuff better or worse? If I dump in all these ions, remember, like dissolves like. I'm making the chemical environment more like calcium phosphate. It's not calcium phosphate, but it's more like it. It's more charged, right? More ions flying around. So that solubility is going to go. It's going to go up, right? Because I'm going to dump in some salt, get it to dissolve. I'm going to increase the chemical environment, make it more ionic. Solubility is going to go up. Right. Okay. But if you use concentrations, you're not going to get the right answer. You're going to say it didn't even change. That's the whole point with activities. If you're going to give someone a drug compound, I strongly suggest using activities and not concentrations, because you want to take into account the chemical environment in their blood. It's not pure. There's a lot of ionic stuff in there. Okay, now it might be really low, so the error might be really small, but if you're dosing somebody, I think it's the way to go. Okay, so that's how you can increase the solubility. Just add an inert salt would be the best word, because inert meaning there's no calcium and no phosphate, right? So you can't have a common ion effect. Okay? Like sodium chloride or something. So this whole talk about chemical environment, ionic atmosphere, these words I'm kind of just making up. I'm supposed to say ionic strength of the solution. That's chem speak. That's what you're supposed to say when you're talking about a solution. And by adding the salt and getting it to dissolve, I'm increasing the ionic strength.
So you're adding the like?
If I'm adding any...
You said like dissolves like. So
like dissolves like.
You're adding like?
Well, like dissolves like, this is what I'm thinking, Kat, in my head. That if this breaks up, I get calcium ions and phosphate anions. Both have a charge. So these guys would dissolve better in something that, at least give it some kind of charge if you can. By dumping some salt and they're getting it to dissolve, we're not giving the solution a charge, but we're increasing its ionic atmosphere. There's ions around, and it's almost like electric fields is what it comes down to. But I don't know if you've had physics. But, okay. So that's what I mean when I say like dissolves like. We're trying to make water more like the compound we're trying to get it to dissolve. So it'll dissolve better, it'll interact better. Okay. But you got to assign a number to it. Because if you dump in a little bit of salt, like sodium chloride, and increase the solubility of calcium phosphate, or you dump in a whole lot of salt, the solubility goes up even more. You have to quantitate this stuff. Well, that's where we have an equation for ionic strength. Okay. So let's see if someone's followed this in the reading here. Casey. 1/2. What's the big sigma? Sum. We're adding stuff up. I is our little counter. Natalie, what's this Ci and Zi? So this is supposed to be the ionic strength of the entire solution. One of these is concentration. 1/2 the sum over I. I is every single ion that's in solution. Every single one. So for every single ion, right, like ion number 1, okay, C1 would be the concentration of ion number 1. Z1 is the ion's charge, right? It's the charge squared. The charge magnifies itself. It's charge squared. It's that much more important. Right? If you have an ion that has a -2 charge versus an ion that has a -1 charge, the ion that has a -2 charge is going to do a lot more damage to the chemical environment than an ion with a -1 charge. So it's charge squared.
Did you say
Okay.
that the sum is over I?
Yeah, over all the ions. So we'll do some down here. Okay. Calculate mu for each solution. So let's write the equation here. Mu, it has to be 1/2. Now add them all up. So we should probably recognize the ions first here. Amanda, what ions do we have in this A?
Sodium.
Yeah, Na plus and Cl minus. Okay, so we should have 2 terms in here. Right? You have to multiply for each ion, multiply the charge times the concentration. Okay, and the charge has to be squared. So what is the concentration of the sodium ion? What would be the concentration of the sodium ion? 0.001. Now, before we even do this, we should probably realize the reason why we can is because, let's see, the solubility rule. This is an odd table. I'm used to a different table. But if you look at all these alkali metals on the insoluble, because you want to know, okay, what makes a solid? Well, if you combine alkali metals with anything, it's always soluble. Always. So these group 1s, these group 1 metals, alkali metals, you can never, ever make a solid with it. If you ever see it, you know it's AQ. Dissolves 100%. So that's why when I asked Amanda, we kind of skipped that. This completely, there isn't any NaCl. It's all Na plus and Cl minus because this is a soluble salt. There isn't any NaCl. It's Na plus and Cl minus. Na plus is a concentration of 0.001. And we have to multiply by its charge squared, so that would be what squared, everybody? Just 1 squared, no big deal. And it's squared, so notice how the negative signs are going to be going away on us. The chloride is concentration of, same thing, 0.001, times its charge squared. So we can get a number for the ionic strength. So if you increase the concentration of the sodium chloride solution, you bet you're increasing little mu, the ionic strength. How about B? Little mu is 1/2 the concentration of, now what ions do I have here? John, what ions do I have if I have sodium sulfate? That's going to give me all what ions? Sodium and sulfate. Sulfate. How do I know? If you don't remember sulfate has a -2 charge, what's the trick to knowing it? The switcheroo thing. All right, I went down there. Okay. So I need to know my concentration, Kathleen, of sodium, and then I'm going to multiply by the charge squared. What's the concentration of the sodium? 0.001? Do you divide by 2 or multiply by 2? Multiply. In fact, if we were going to write how this guy breaks up, we should really write a 2 there, right? Because it really breaks up into 2 sodiums and 1 sulfate. That's probably how we should have wrote it. So it has to be double 0.002 times the charge squared. And then the concentration of the sulfate, everybody, is 0.001, because there's just one of them. Right. And times its charge squared, which is a -2 squared. And then you do the math, and you'll get a number for the ionic strength. Okay. So just remember, it's ionic strength. You can actually get a number to measure this ionic atmosphere, this chemical environment with ions. It only works for ions, right? Because if you have something that doesn't have an ion, something that doesn't have a charge, what's Z? 0. So those terms, you could have other stuff in the solution. You should really, that little sum I shouldn't be over just ions. It should be over every bloody thing in the solution. But a lot of them are going to be zeros because they don't have a charge. Yes?
Can you get a negative?
No, because it's always charge squared, and concentration can never be negative, right? So your mu is always going to be positive. Okay. So I said that we're supposed to be using activities all the time. So let's get into that then. What is the concentration of a compound? When is the concentration of a compound the same as its activity? When the compound is, or it has no charge. And the compound's neutral, or it has no charge. There's nothing to do. The activity is the concentration. Okay. So you're not going to have very many homework questions that have solutes that aren't going to have a charge. There's nothing to do there for activities. There's no charge. Compounds without a charge. They're neutral. Neutral's the word, right? Neutral compounds. Fructose, benzene, cyclohexane, all those organic compounds that those guys over there work on. But remember though, biochemistry, there's a lot, so many things have a weak acid. That's where the chemistry really comes into play in a lot of things for weak acids. Now you got a charge. For one form, for that conjugate base if it's a weak acid. So you can't always ignore it. Is it better to use activities or concentrations in the real world? Well, we kind of talked about that. And here's how you get activities. We're going to, in our equilibrium constants, in KSP expressions, Ka, Kb, Kw, it doesn't matter. Whatever you're writing, and you want to write concentrations, where you wrote a bracket and wrote it to its little power in the reaction, we're going to use A's. Capital A, and the little subscript is going to be what the compound is. That's all we're going to do. Replace all those things. Now, what is this activity? The activity of some compound C is its concentration times, what's the Greek word for that? Gamma. Okay? So we're going to have to, all they're doing, when you look at this from, if you take P-Chem, this happens a lot. We want to use the same, everything we've been doing so far. We don't want to relearn how to write an equilibrium constant. We don't want to relearn how to write a reaction. We want to stick to the same format. So all we're going to do is we're going to use our concentrations, but multiply them by a fudge factor. So we get the right answer. Those gammas are, well, in my words, fudge factors. But you're not going to hear that. They're calling them activity coefficients. But they're just fudge factors, so that you'll get the right answer when you start messing with salt, adding inert salts to solutions, or taking into account the chemical environment. So what would be the activity coefficient if the solution were acting ideally? Well, I guess the activity should be the concentration, so little gamma should be 1. Right? So ideally, and that's what we've been hoping this whole time up to this point, is that everything's acting ideally, so we can just use concentrations. We've never used the word ideal solution. So you've been in an ideal world all the way up to this point. Now you're seeing, now your eyes are being opened. Okay, here's something that I added here. Write the KSP expression with and without activities. Okay, so the KSP reaction is already written for us. But if we do it without activities, it would just be 1 over concentration of, oh no, products over reactants, not 1 over, right? It's going to be all over 1, right? Products over reactants. So it'll be concentration of Pb plus 2 times, everybody, iodide. Concentration of iodide, but squared. Okay, that's how we've been doing it. All I'm saying is you look up the exact same KSP number And we're going to write it in terms of activities. So you're at a big A for each one, right? One of them has to be for the lead. The other one has to be for the iodide. So there's my one for the lead. There's my one for the iodide. Just make sure you do what for the one for the iodide? Square it. So that's all we're changing. We're just replacing concentrations with activities. This is what it means. Okay? So, and then if you wanted to keep going, I guess you could write, what, the concentration of lead times the gamma, right? Its fudge factor, that one, and then times the concentration of iodide, but this guy has to be squared, and its activity coefficient squared, right? So that's what it's really saying. And these concentrations of lead and iodide, it's the same as we always were before. Okay.
You square gamma too?
Yeah, because that concentration of iodide, sorry, the activity of iodide is squared, so that means it has to be concentration of iodide squared and its activity coefficient squared.
So what is the gamma? Like
Okay, yeah, so these guys got to be numbers. How do you get them? There has to be some way. There's two ways. Turn to the next page. Tune in next week. There's two ways. Okay. This way, I don't know why they even give you ways that you don't use. But they do, so I'm giving it to you too. Here's one way. You plug in all this stuff. Now you recognize mu. That's the ionic strength. So it's nice. You kind of plug in it. You don't need any tables. Well, I guess you do. Kind of lying. The Z is going to be the... What's the Z? Z is the charge. At least they're being consistent. Mu is the ionic strength. Z is the charge. We already have an equation for mu, so we have to calculate it, plug it in. So if we're going to calculate, I don't know, just pretend, the activity coefficient for iodide, right? You'd plug in the ionic strength of the solution. Now the charge is -1, so it'd be -1 squared for Z. The only funky thing is that darn alpha. Alpha is the, does anybody know? Radius. Yeah, the hydrated radius. And sure enough, you have to look it up for different ions. So you can't get away from the tables. Okay. Seems like a lot of work when you can just use a table in the first place, and that's all we're going to do. Okay? But the homework might give, I don't know, they might have you use Dubai, Huckle, but I don't know. Okay. So, and I didn't have a chance to scan the tables, so we're going to have to find one. Let's see, what chapter are we in right now? Chapter 8. Did you find one?
Yeah, it's in there. Right by pH.
Oh, here's some activity coefficients, but there's a big table of them. There's a bunch. Can you see this? It's on page 144. There's a whole bunch of them on page 144. Now, if you take a close look, I mean, all the ions known to man aren't listed there, but a lot of them have the same values, same fudge factors, the same activity coefficients. For example, our iodide is grouped with other things, other anions. How? Well, according to Dubai Huckle, they just must have the same what? The same. Well, ionic strength is something we're going to have to look up and calculate because we're going to have different activity coefficients according to the table for different ionic strengths. But two ions could have the exact same coefficient. Yeah, you're right. They have to have the same ionic strength, but they have the same alpha, right? And charge too. Because if they're in the same solution, they're going to have the same ionic strength. Because that's right. Everything in the solution has the same ionic strength. You calculate it over everything in the solution. So mu would be the same for two different ions. If you want two things to have the same activity coefficient or fudge factor, they have to have the same Z, same charge, and they have to have the same alpha, hydrated radius. And that's why they're kind of, you don't really need to know that, but that's why they have the same, that's in the same column, same row when you're reading that. Okay. So I got to get that scan and get that in there. But let's take a look at this. Oh, so we have to hand this out. I'm going to hand it to Anna here. Okay. Because if I were you, I wouldn't bring my book to class either. Right? What's the point? Okay. So Anna's going to look at this. It'd be a lot better if I could have scanned it, but I didn't get by with it. So I'm asking Anna to find the activity coefficient, my little gamma, for magnesium ion. And I guess, we went through some work and we calculated the ionic strength, but the ionic strength of the solution is 0.05. What's a number for gamma? Did you find it?
Yeah.
Okay.
0.755.
Oh, 0.05 is the ionic strength, though.
Yeah.
So it's going to be what?
0.52.
0.52. So what she did, she found the ion in the table, right? And then she just went across and found the column that had the right ionic strength. The ionic strength is listed up here. Okay. Oh, it is?
Yeah.
No way.
Day 14.
Oh, we're not there yet.
Yeah, but it's
Oh, you guys are, though.
still in the table though, right?
Nice, yeah. There it is. Okay. These pages should be numbered. But on day 14, there it is. So you guys will have it. So did you see what, Anna, you said the number was what? 0.52? Did everyone see it? Show her, Miranda, where she got it. Make sure you can read that table. 0.52. Okay? Make sure you can read that. Okay, so now we are, I'm going to mess with the next one here. Okay. Now do the same thing. Find activity coefficient for hydrogen ion at 0.003. Ah, it's supposed to be a gamma. Right? It's not in the table, right? So I got to... Oh, I have the table. I can look at it here. Okay. There's the word that no one likes, Kat. Interpolate. We have to interpolate. Here's our interpolation equation. We're going to have to interpolate because we first verify, right? It's not in the table. Now, you could guess, but that's not going to get you very far, and you get sued if you're in real life, so can't guess. Unknown gamma interval over the known gamma interval. So I think we need to write down some stuff here. What interval are we talking about? So let's find hydrogen ion. Right? Okay. Oh, there you had thanks, very, very top. Okay. So we should probably, what can we do here? We want to know strength. We have we want to know 0.003. So that's my mu. Here's my gamma. God, my gammas look like. We want to know what it is, right? I'm just trying to write it in the middle. I'm going to write numbers on the other side so you can kind of see what the intervals are, right? Like 0.003 is what we're after. We want to know what gamma is. So I just wrote a little question mark under it. So I'm going to pick a point less than it. And the ionic strength less than 0.003 in the table is 0.001. So we'll write that one right here. Now the ionic strength that's bigger than 0.003 is 0.005. Okay. So do you see what I'm trying to do here? I'm trying to help you identify, or for myself, identify my known interval. Right? For our ionic strength, it's going to be 0.05 minus 0.01. Right? That's the known interval. Right? Let's do the same for the gamma. Right? For the activity coefficients, at 0.001 for hydrogen ion, the activity coefficient is 0.967. Make sure you can see that. Right? That's 0.967. What is it for 0.005?
0.6. 0.2. Oh, 0.93.
Yeah, isn't it 0.933?
Yeah.
Okay. Okay. So now you have to be consistent how you're going to do this. Okay. Well, let's do the known intervals first, I guess, right? The known activity coefficient interval, right? If you want to take this one minus that one, fine, right? Because it's bigger. .967 minus 0.933, okay? And the known ionic strength interval. Now notice I took 0.967 minus that one, so I should probably do the same up here. 0.01 minus 0.05. If you kind of mess up, turn it around, all it's going to do is give you the wrong sign. Activity coefficients have to be what? Positive. Look at that table. They're all positive. So if you end up doing your calculation, you get a negative, don't worry about it. Just erase it. You're going to get numerically the exact same thing. But it will work out every time if you're consistent. We did 0.967 minus 0.933. Okay, so let's do 0.001 minus 0.005 for my known ionic strength interval. Okay. Now my unknown interval, here's where I think you can mess up. I want to do this question mark minus 0.967, or 0.967 minus the question mark, right? That's one choice. Or, right, the question mark minus 0.933, or the 0.933 minus the question mark. See how there's two different choices you could pick. But if you pick, whichever one you pick determines how you pick the interval up there. Let me show you. It seems to be easier just to go from left to right. So I'm going to pick my unknown activity coefficient interval to be 0.967 minus question mark, or x, whatever you want to call it. Okay. That means then that my unknown ionic strength interval has to be what? What would you write? 0.001 minus 0.003. You see where the one place I think you could screw up? Okay, one more time. First thing we did when we have to interpolate, we looked and see if we could get it in the table. We can't. Okay, interpolate. So just remember, this works for everything. Whenever you're interpolating, it's the unknown interval over the known interval, right? And write out your points. First write out what you're looking for, right? You're going to be given a table of these things. Put an 003 in question mark. Those are the two things I'm interested in: the ionic strength and the activity coefficient. And they're always XY points, so you write them down, and then you write down. And once you make this nice table, it's easy to pick out what's above and what's below my unknown area, my unknown point. So for me, writing these 3 points is key. Otherwise, I get so lost, so easy. Okay. And then just be consistent with your intervals. Okay. Like if I'm going to pick my unknown interval to be 0.967 minus question mark, my unknown interval for the ionic strength has to be the same order, 0.01 minus 0.03. Okay. And then you do the math and you get your question mark. And I don't know what it is, but hopefully it's going to be somewhere around 0.95 or so. Okay, so that's what I would do too, is I would go through the math and get your answer and then see if it fits. If it doesn't fit, you messed up. Right? Okay. And did you get an answer? It is 0.95? Wow, I guess pretty good. Okay. And it fits. So we're done. Okay. So that's interpolating. For non-ionic compounds in water, hit on this one more time. You're Andy. The activity coefficient, or fudge factor, always equals 1. Right. And if you're not sure where she's coming from, she's exactly right. Where's our equation for activities? Here it is, right? If it doesn't have a charge, there's nothing. It doesn't care. It doesn't even know what the chemical environment is. It doesn't interact with ions, ionic atmosphere, chemical environment. It doesn't matter. So you want this guy, the activity coefficient, to go away and just be 1. So activity equals the concentration. So she's right. Activity coefficients, fudge factors for all non-ionic or neutral compounds is always 1. The activity equals the concentration. You can't really mess up. Okay. So we have time. The a direct application of this is, and you can sound smart, by the way, doing this, because me and organic don't get along at all. But you go to these meetings and all these people are talking and there's posters and things, and the guy was trying to get this big, funky, biochemical big thing to latch on to something else. I don't know what he was. It wasn't DNA, but it was some biochemical thing. And it was doing it all in a test tube, and it just couldn't get it to work, couldn't get it to work. So you want one thing to interact with the other. That fits perfect. And we just talked about this in class. That's why it was fresh in my mind. Did you mess with ionic strength? Very easy thing to do because you just dump in a little bit of salt. Wow, that's a great idea. I should try it. See? And I don't know jack about what he was talking about. But I know that you want one thing to interact with another. Messing with ionic strength is really, really powerful. Okay? So, okay, let's take a look at this. Calculate the ionic strength of some solutions here. Assuming complete dissociation at this low concentration and no hydrolysis. Okay, well, I guess we don't worry about it. You just want to make ions. Recognize what the ions are. Right? Write down the equation for ionic strength. Right? So you're going to need to know every ion's concentration, every ion's charge, and sum it up. Right? Try it. See if you can get it. Right. Go back and look up what the ionic strength equation was. Right? And so mu is 1/2 the sum concentration times charge squared, something like that. Recognize what the ions are. And whether you know iodate is IO3 or not, it doesn't really matter. You recognize polyatomic ions, subscripts, what they mean. See if you can get it. Anybody get an answer?
Yeah, I don't know if that's right.
001. Might be. I don't know. What did you get?
I haven't done it yet.
Faster, faster, faster. There's a .0012. Someone else got .0.
I got .0012.
.0012. Natalie, what'd you get? Not that? Okay. Recognize the ions. That would really help. It's going to be La with what charge? A 3. Do that switcheroo thing. Right? And then it's going to break up into how many of these IO3 minuses? 3 of them. If you recognize that, then I think it's pretty straightforward. It's going to break up into La plus 3 and 3 iodates. Times charge squared. Right? And then I hear folks are getting like 0.0012 or something. Okay. Let's see if we can mess with these tables. Find the activity coefficient for sulfate. Ionic strength is 0.01. It's got to be in that table. Yeah, okay, it is. It's just making sure we can read the table. So flip over to your activity coefficient table. And day 14, I don't see sulfate in there. Oh, they're kind of organized, right? By charge. Look in the stuff that's plus or minus 2 for sulfate. And then, Amanda, you got what? 0.660. Can you find it? Okay. Last one. Okay. 0.03 must... Didn't we just do that? 0.03? Oh, that was 0.003. All right. So find the activity coefficient for hydrogen ion when the ionic strength is 0.03. Now realize, just again, realize you have total control what ionic strength is. Because you just dump in some salts and you know what the concentrations are. So ionic strength is something you have total control over. That's how you can effectively really be messing with things. Okay? In a very simple and straightforward way. So use the table to get the activity coefficient of hydrogen ion. Notice this would even change the pH, right? Because remember the equation for pH? This is what we're going to do next class period, but pH is the negative log of hydrogen ion concentration. BS, not true. pH is the negative log of the A word, activity of hydrogen ion. That's how you get pH. Very different. Okay. So identify your unknown point. Write down points above and below what we're looking for. Right? Kind of set it up. I'd set it up something like, right? I know my mu is 0.03. This is the guy I'm after. That's how I set up my table. Put a point above and below it. We're running out of time, but we have about 1 minute left. See how to do it? You got it? What did you get as an answer? 0.887. Did anybody else get that? Oh, okay, Casey got it. I bet you that's right. I'm going to scribble that down. If 2 people got it, I bet you got it. Hopefully you came up with 0.887. So have a good day. Come by. I'll be glad to help you out with this stuff. See if you can make the open house tomorrow.